We focus so much effort on training models, getting features, on all that crazy architectures. The space of models is that we can consider is increasing like rapidly, but we still are bottlenecked on like, is this model better than the one that we already had?
You're listening to Gradient Descent, a show about machine learning in the real world, and I'm your host, Lucas Bewald. Today I'm talking with Sean Taylor, who's the head of Rideshare Labs at Lyft. Previously, he was a research scientist on Facebook's core data science team, and before that, he got his PhD in information systems at NYU's Stern School of Business. He also has a BS in economics from the University of Pennsylvania, and he tells me that he prefers R to Python. So I'm excited to get into that with him today. I guess where I wanted to start is the stuff you're working on now on ride sharing at Lyft. I mean, my first question is just like, for people who haven't thought deeply about this, like how does data science and ML factor into a ride sharing app that probably everyone has used? Like, what are the pieces that matter, and what role does data science and ML play?
Yeah, that's a great question. I think it's a pretty abstract concept because you just sort of tell an app where you want to go and a driver shows up, and there's a lot of things that happen under the hood to enable that. I think of Lyft as like a stack of algorithms that sort of like all add up to a driver arriving like when and where you want. So that driver showing up there is just a sequence of like well-made decisions and you can trace those decisions back as far as you want, all the way to like when we acquired that driver and signed them up to drive for Lyft, and when we acquired the rider and got them to kind of install the app and decide to use it. So there's all those decisions added up to like that match that we got in the marketplace. On the actual matching at the time of the ride request, I would think about it as like, well, there's the map. We have to have a high quality map. On top of the map, we come up with ETA estimates. So how long will it take a driver to get to a rider? That helps us perform a more efficient matching. Then there's a dispatch algorithm, which actually performs the matching. So there's a wide set of available drivers for some ride requests. So we have to decide like which one is the best driver to send. And then also there's just like, we have to decide on a price. So there's like pricing is a kind of core algorithm for Lyft. On top of like planned pricing, there's adaptive pricing. So like, we have to kind of respond to marketplace conditions to try to make sure the market stays liquid. So that's an algorithm that we have to run. And then I guess on top of that, we have like, we'll give drivers incentives, we give riders coupons. So there's algorithms to decide like, how we disperse those. So it's just like a wide variety of little mini algorithms, all the way down to just like now we have, say, like we're predicting where you're headed so that when you open up the app, maybe we can be intelligent about what shows up on the screen. So it's a lot, and I think like a good experience is like the conjunction of all those good decisions made. So if any one of them goes wrong, it sort of can be a very bad experience. So I think of the Lyft problem as more of like quality control in a way. It's like the product itself is pretty exchangeable. Like we have competitors. You have other ways to get where you need to go. So really, it's all about like making sure that those decisions are made really reliably. Every one of those decisions is powered by some estimate of some state of the world, right? So like the ETA estimate is probably like the most tangible. It's like how long is it going to take a driver to get to a specific spot on the map right now? But we have to estimate all kinds of other quantities of interest, like how will riders respond to higher or lower prices? How will they respond to higher or lower wait times? Or all sort of like combination of like machine learning and causal inference problems in a way, because like ultimately at the end of the day we're going to like change something, and we don't want to just train on it's not like a supervised learning problem. We actually want to say like, what would happen if we did this differently? What would happen if we sent this other driver instead? And so the problems are quite a bit more complex than just like a standard kind of like predictive modeling setup.
So, I mean, how do you think about that, right? Like changing a price is such an interesting thing. Like it doesn't fit. Definitely, I agree. It doesn't fit neatly into like a sort of normal ML prediction. Like, do you have training data that you can run on, or how do you even model that?
Yeah, it's a super interesting question where you have like one way to think about it for machine learning people that I like way to explain it is like that there are features that are not under your control, and then there are features that are under your control, and you want to sort of think about modeling them differently. And it's important that the features under your control are subject to some randomization in order to be able to kind of estimate a causal quantity of interest. Like if you really want to know what's going to happen when you raise prices, like you have to raise prices sometimes. And so part of the problem with training models like that is you have to let the causal part of the model speak a little bit more than the features. Like there's going to be other things that predict conversion rate on a ride much better than price. Price is a powerful predictor, but if you don't randomize it, then there will be other things that could explain the change in conversion rate that are correlated with price, like say ride distance. So controlling for a rich set of things, having randomization of the variable is really important, but also just sort of there's a whole bunch of modeling architectures that we employ that help kind of let the causal part of the model speak a little bit more. There's some really exciting work going on in say people call these heterogeneous treatment effects models, and there's even neural network architectures for doing these kinds of things these days. But at the end of the day, you have to have been running some experiment in the background in order to kind of make those models be able to tell you what's going to happen when you change the state of the world in some way.
And I mean, I would think price specifically is obviously a sensitive topic for users, but also probably even way more for the driver. Do you think about other considerations there? Do you put constraints around yourself around setting price? Outside of just modeling the sort of most efficient market or something like that?
I think that one of the core problems for Lyft, and it's very pervasive, is what's your objective function for the business? You have to at some point, you have all these algorithms that are all working together. What common goal are they working toward? And at the end of the day, there's some kind of welfare being created by the system, and it's going to be allocated. Some of the welfare is being allocated to the rider, some to the driver, and some to Lyft, which we'll take as profit. So we have to figure out where we're going to split those things, and there's trade-offs in splitting them different ways. If we just greedily took all the objective for ourselves, we charge really high prices, pay the drivers almost nothing, and no one would use our platform. So there's these short-term, long-term trade-offs. So finding the right balance there is really important. One of the ways that we do that is we have a lot of guardrails in the system. So we'll say we would really prefer if certain things never exceeded some tolerances, and that's sort of a way of us heuristically applying some guidelines that help the algorithm stay in a safe place. For driver earnings, for instance, we really like to increase driver earnings as much as we can. One way to do that is to just have people pay more. A better way to do it for everybody is to improve the efficiency of the system. So if we can get drivers to be, have a passenger in the car more often, then they just make more money, and the total surplus is greater for everybody. So that should really be our goal. So when we think about pricing, it's the zero-sum game version of the thing. We would like to make the sum of the game larger for everybody, so we split a bigger pie. So a lot of our algorithmic improvements that we think about are more on the efficiency side than they are on can we take more money from this person and give it to this person, because that just you run out of options there very quickly, and you end up in just sort of somebody's unhappy.
Right, that makes sense. I guess, probably a loss function that everyone can relate to is the ETA estimation, right? We've all kind of been in a rush and had, a car come late. And you had a really nice post about this and thinking about what the right loss function is. But I wonder if you could sort of say how you think about, what it means to have an accurate ETA function.
Yeah, I think that's a fascinating statistical topic. I mean, that post was about there's a wide space of loss functions that all sort of have some desirable properties of producing an unbiased estimate of ETA. You might even think about applying a bias estimator. So I don't care about getting it accurate. I care about giving the user an upper bound or something like that. So you could think about some kind of quantile loss. But ultimately, ETA predictions are inputs into some downstream algorithm. So we've decomposed the optimization problem into pieces. And so the ETA estimates are sort of a thing where we have to have a contract with the dispatch system, which is that our ETA estimates have some statistical properties. So unbiasedness is a really key piece there, because we're going to run an optimization on top of those predicted values. And if we say hey, we're going to add a little bit of buffer on top so that the rider doesn't have a bad experience thinking that we underestimated, that would be bad for the downstream optimization. So sort of the algorithm consumption of the estimates and the human consumption of the estimates are a little bit at odds in what would be desirable. So I think we tend to prefer to get the statistical unbiasedness right, and then figure out how to make the user experience better in a separate layer as much as possible. I think that historically we played with displaying ranges of ETAs. So sort of a better answer to this question is not estimate the thing differently, but just be honest about the distribution of errors that you're likely to make in practice.
Sure.
Yeah.
Well, tell me this: what loss function do you use? I mean, unbiased could mean different things depending on the context, right?
So I personally haven't worked on our ETA estimation problem. We have a really strong team of researchers there doing some really interesting stuff. I haven't worked on it, so I don't know what we landed on. I know
No.
that we're at the point now where it's pretty hard to eke out gains in that algorithm, and I think it's like a thing where most of the effort is on just like accuracy. And one of the super interesting things about ETA is that not all accuracy is equal. So being correct about ETA in certain situations is like more pivotal for your downstream optimization than others, and so you might think of that as like label weights in some way. So there are cases where getting the ETA right could really make the difference between getting the routing decision right or wrong, and cases where like you're basically going to do the same thing either way.
Could you give me an example of that? It's hard for me to picture when, I mean, of course, that's sort of the situation for any algorithm, but what's a case where ETA is super crucial?
Yeah, so say that there are two drivers that we could potentially route to a rider, and if the in cases where the estimates end up being ordered the same, then the estimates aren't pivotal, right? So like there's a wide class of estimates that would rank them the same, and so always dispatch the same driver. And then but in markets where we have a lot of options and there's lots of drivers available, then you start to make mistakes, right? So it's kind of like a ranking problem, and if you invert the ranking because the estimate was like off in some cases, so in thicker markets, we have opportunities to do better. We have opportunities also to do worse because we're getting the ordering of the drivers that's like efficient to send wrong.
I see. Interesting.
There's also a weird bias problem in the data that we have for ETA. So we only observe the drivers that drive certain routes. So they only drive to places that they've been routed to. So estimating the ETA for segments of the road that we don't observe drivers on is like it's a set of like missing data. That missingness is not at random. So we don't like they might not be driving a certain place because we're not routing them somewhere because we think the ETA estimate is really long, but it could now be short. So there's like a sense in which like you'd prefer if you collected your data under a little bit of extra randomization or noise to get a better estimator. So it's kind of like an interesting like bias training set problem that I think is a little underrated. We haven't quite figured out like what to do about that.
That does seem super tricky, and I guess it's probably hard to run random experiments to collect more data. I think that might make people frustrated.
Yes, that's right. It's very analogous. I mean, I used to work at Facebook. One of the things that you'd worry about is like you're ranking a story really low in newsfeed, and it just no one ever sees it, so they don't engage with it. So your training algorithm doesn't know that there's some features in there that could say like, "Hey, this is really good. We should be displaying this at the top." So you can end up in these feedback loops where some friends of yours might not ever see their posts again because they just aren't getting any eyeballs on their posts anymore. I don't know if that actually played out at Facebook, but it's super similar sort of problem is that you have to acknowledge that your training data isn't some random sample of what you're looking for.
Right. I guess when I look at the rideshare challenges that you mentioned, they seem like situations where you have pretty structured data coming in and maybe lots and lots of data, and you have to deploy into like a high volume production. It seems like a case where neural nets might struggle a little bit. Like, have you found that mostly neural nets work better than maybe kind of older? I guess older is the wrong word. maybe like less complicated algorithms.
I would say so. We do have a kind of like a bias for simpler solutions, and I think that's for good reasons of like needing to keep things reliable. And so historically, people at Lyft have gotten a lot of successful results with tree-based models. So things like LightGBM and XGBoost are pretty popular techniques for supervised learning problems, and I think that's for good reasons. I think trees do well with geospatial data, like latitude and longitude and time are things that trees can find good segmentations of, and so like the features are naturally encoded very well by the representation is learned by tree very effectively, and so like neural networks might provide like a boost over that in the long run if you had like a lot of data, but you have this thing that learns really quickly and doesn't overfit too much, and so it's like an easy drop-in thing to use. I think that we're moving toward using neural networks in some cases kind of gradually, and I think we are trying to sort out some of these like deployment challenges and making sure that they run reliably. And I think all the kind of model quality control stuff is something you have to relearn a little bit as you move to a new modeling paradigm.
I guess you mentioned online at one point that your team uses entirely PyTorch. Is that right? And could you kind of talk about the trade-offs there?
So part of it is historical. I worked at Facebook, and I did a hackathon at Fair, and so that was right when they were deploying PyTorch for the first time. So I learned about it before TensorFlow. So it wasn't like I thought PyTorch was better than TensorFlow. Fast forward to last year, my team was working on, we're building a forecasting tool that has a plan built into the forecast. So we can change some policy variables and have the forecast reflect the change. So we might say like, hey, we increased our couponing volume, and so that's going to increase demand. And so we'd like the forecast to reflect that. So it's sort of like forecast with some causal effect baked in. If you can produce a forecast like that, one of the natural things that you'd like to do with it is actually run an optimization on top of it. So you'd say, I will produce this forecast and then actually optimize the plan to make the forecast look as good as I would like it to look. And so if you're doing that, a really desirable property is that the model that you fit is the differentiable object, so that you can use basically the same methods that you use for optimizing the fit of the model, you can use for optimizing the policy variables that you're plugging into the model. So we really wanted to be able to produce like a Python function that we had fit from data, but that was differentiable. So having the model be done in something that was autogradable was really important. So I'm a big Stan fan, and I like Bayesian modeling, but a lot of the Bayesian modeling tools don't naturally like just produce this object that is differentiable. So we're like, okay, well, we should work in some space where we had these autograd tools available. It's been a bit of a trade-off. I think we're doing things that look a lot like Bayesian models, but on top of PyTorch. And so we're having to kind of like invent a lot of ways to do that ourselves that would have been a lot easier if we did something like PyMC or Stan. And so it's been a little bit of a challenge, but the upside has been a lot of modeling flexibility, and also the ability to kind of like borrow from what all the neural network people are doing for improving the speed and reliability of fitting. So that there's a little bit of like, it's fun to do things that look like neural networks, but are not. Like, we're not using them to fit. Like, there aren't any layers or pooling or anything interesting going on. They're very similar to just like the kind of models that you would fit in R. But we really needed this like engineering requirement of like that we would produce this model that had this nice property of being able to run optimizations, and getting the gradients is like a really beautiful thing at a place like Lyft, because we care about marginal effects of everything. So if you want to know what the lifetime value of getting an additional rider is, which is a very common thing in business, like what's your marginal benefit of getting like one more person on the platform, with a differentiable model, it's very easy to do queries like that. We can sort of just say like, what's the gradient of the total lifetime value of Lyft, which is something we can estimate with the model. We can do the forecast, add up all the future revenue, discount it, and then just like actually just look at the gradient with that variable with respect to like a rider activation and say what that is. And so PyTorch was a really natural fit for doing those kinds of queries. So yeah, it's a little bit of like, we got really low level to solve a problem, and I think sometimes we regret being that low level.
That's so interesting. So it wasn't PyTorch versus TensorFlow. It was PyTorch versus like a Bayesian framework, and it also sounds like you're using PyTorch essentially for data science because you want the sort of like autograd, or do you want the gradients to be able to pull them out? I guess where have been the pain points? Like, where has that felt frustrating compared to what you've done in the past?
I think part of it is that we bet on the optimizers that are used for neural networks are not particularly great for some of them. A lot of the models that we fit are pretty small, fit into memory. We should be using some second order methods. So like, we kind of were like, we've struggled a little bit with like, confirming that we're at a global optimum for the model, when if these are models that we should be able to confirm that. So if we had done it in like more traditional model package, then we might have ended up with like a more stable optimization procedure. I think the modeling flexibility that you get from PyTorch is partly a cost that you pay, is that everything's pretty low level unless you have these higher level abstractions. So we had to build a lot of those abstractions ourselves. So things like building spline basis expansion, and building like ways to we actually have 40 or 50 models that compose together. We had to build a way to compose a bunch of models so that they become like one big graph of models. We had to build a lot of that stuff ourselves. We have a couple people on the team that just got really interested in that part of the problem. I hope that one day we can open source the modeling architecture. The other super interesting pain point that caused us to develop something that I think was pretty interesting was that everything in our system is a tensor. And tensors are really natural representation of marketplace data because it has a regular structure to it. So you could say like geography and time are are 2 dimensions of the tensor, and you might add other dimensions. And that neatly encapsulates a lot of the kind of data that we capture. We ended up kind of creating like a labeled tensor implementation that we find it really useful. Sort of like it's kind of like a tidy data frame in R, but it's a tensor, and so we can use them as just variables in the system and compose them and multiply them and do operations on top of them. And I later found out that there's this like kind of label, there are a bunch of these like labeled tensor packages out there that do similar things. And so I think that was something that we didn't realize we needed to build, but keeping track of all the dimensions of all the tensors that we were passing around became sort of like a first class problem very quickly.
It almost sounds like you want to use data frames, right?
Yeah, they're data frames, except that they're dense, right? So you can guarantee that you always have for any pair of coordinates, you always have a value. So it's like a special class of data frames where you know some properties are true about them.
I guess this is a more open-ended question that I hadn't planned to ask, but I mean, since you've done a lot of Python and R, I'm kind of curious, like how you compare the two. Like if you have one that feels more natural that you like to live in, or
yeah, I think this will probably be pretty controversial, but I do everything in R until I can't anymore. Because
that is controversial. Interesting.
I think that the tidyverse people have figured out a lot of the interactive data analysis stuff. That it's much more kind of first class in R. And one of the things that's an interesting consequence of R syntax is that the lack of white space sensitivity and some of the ability to kind of just like use unbounded variables means that you just have a lot less typing to do kind of similar things. I also I'll poke fun at Wes because I've had this conversation with him. I think the Pandas API could use a little love, and like if we could reinvent Pandas from scratch and do Python data frames again, we'd probably do it a little differently, and something with a little bit less surface area for developers and I think that in Hadley is sort of a designer. Hadley Wickham is like the creator of dplyr and a lot of the tidyverse packages. I think like he thinks really deeply about these micro interactions that people have with the code. Like, what are you actually do? What are you trying to accomplish? What's the minimum like way to get there? And then also, is it going to like stick in your brain? Are you going to remember to do it next time? So I've just found that sort of fit my brain a little better. But all the production code that we write at Lyft is in Python. So I find myself sort of like porting some of my analysis in R over to Python quite commonly.
Can you give me an example of where data frames frustrate you? Where Pandas data frames are frustrating?
Sure. So one thing that is a little annoying is having to so some of the operations will emit data frames, some of the operations will emit a series depending on what kind of aggregation that you're doing. So this is sort of like a functional programming no-no, right? Like and dplyr is designed the opposite way, where there's a very standard interface. Like most of the functions take a data frame as the first input and always return a data frame. And that allows you to do this kind of like chaining kind of thing. So if you look up method chaining in Pandas, you'll find a couple of good articles on how to do it. It's a real stretch to do chaining in Pandas, where you can kind of apply a series of operations and read through them. And you can do this, but it just doesn't like look as readable, and it requires a lot of like clunkiness. The dot pipe operator in Pandas is something that I use a lot when I'm using Pandas, because I think it sort of like does what I like about dplyr. It just requires a lot of you to write your own code to fill in some of the missing pieces. I think reshaping data frames from like long to wide is just like dramatically easier in R, because that interface is a little bit simpler, like stack and unstack operations. In Ruby, they call it like principle of least surprise. It's like you should always, the API should return something that is like unsurprising to you. I think sometimes some of the stuff in Python is like most surprising. Like you're like, how did I get here with this object? I have no idea. This is a long rant and a long complaint, but I think it's like we can get there. There's plenty of great Python developers that are working on this, but I think that we made some design decisions early on that made it a little bit challenging to create these expressive interfaces.
It's so funny. Like, so my experience was I wrote code in mostly R for years, and I always found R a little baffling. And when I switched to Python, I was so happy, and it made so much more sense to me. And so it's really interesting that you feel exactly the opposite. I wonder what's different about our brains, or what we were trying to do. Like, I think maybe functional languages are more natural for you, and I feel like all my smartest friends, that's the case. So maybe that's what's going on. I mean, the thing for R that I always missed was I just felt like the plotting was so much more natural than Python. Like I feel like I still have to look up Python's plotting stuff. So it's interesting that you don't even mention that as an
Yeah,
issue.
I hate matplotlib a lot. I would complain about that to anybody. I think Altera really solved that problem for me.
Interesting.
Jake Vanderplas wrote a really nice package. It's very ggplot like in concept. In syntax, it's a little different, but I think it's a close map, so it's pretty easy. But I had the opposite. I was a Python developer since 2004 through grad school. Like I spent a long time in Python. I started learning R in grad school. It was like my later language, but I like it more. So yeah, maybe it is just like some people have a certain kind of brain that fits one thing or the other.
Well, cool. I also wanted to ask you about the the profit project that you worked on at Facebook. Could you say a little about what that did and why you made it?
Sure. Profit is a time series forecasting package. It was built because we had some applications internally at Facebook that we didn't have good tools for. At the time, I was on the core data science team, kind of like looking for interesting high impact problems to work on. And we had a couple people come to us and like just with forecasting problems. And I looked around. I was like, forecasting can't be that hard. And I started to like Google around and look for what tools are available. And I really felt like the tooling landscape was a little primitive. And in particular, there's one interesting aspect of business time series that's like just difficult to model traditionally, which is this multi period seasonality. So you have like a yearly cycle in data is super common, a weekly cycle is super common. So you just end up with like needing to think about carefully modeling these kinds of, they're just features, they're just that can be extracted from time, but they're not easy to do in like an autoregression or like exponential smoothing kind of framework. So I worked with Ben Leatham. I have to give a great call out for, because I think he invented all the important stuff in Profit. So we like that project was going really poorly until Ben got involved and helped me solve a couple of really key problems there. And then what we figured out was that like we just had this like class of time series problems that are really common in practice. It's actually a really constrained modeling space. So it's almost like an architecture for time series models. It's like we just said, hey, like there's a small set of models that capture a lot of data that we see in practice, and that prior over the models is a really useful thing to know, because it means time series data are always data constrained. You might have a year, you might have 300 observations, 400 observations. You're not talking about like something you can learn a lot from the data. You have to bring a lot of priors to a time series problem. So by coming up with reasonable priors for what that should be, and if you look at the Profit code, it's got like hard coded parameters that are like our priors over what we think is likely to happen in like it's not an elegant model in the sense of that it's not super general. It's actually very specific, but that happens to work well in practice. So sometimes I just call it like a bag of heuristics that we cobble together. And I think real time series modelers probably get a little frustrated with us for like having empirical success from something that's not as principled as the work that they've been doing. But people get a lot of value out of it. And part of it is just that like they don't really want to learn about time series modeling that much. They'd prefer to just like get it done and move on to another problem. So Profit provides a
So
pretty easy way to get there.
I have a feeling a lot of people listening to this might find this useful. Could you say kind of what's the case where Profit's going to do well and where it might not do well?
Yeah, so Profit is built on sort of like a lot of like local smoothness assumptions. So like, if your time series jumps around a lot or is very random, or it has a non-human periodicity to it, then it's unlikely to work. So it's really designed for these like human generated time series, human behavior generated time series. So like web data where you're counting how many visits come to a website is like bread and butter for Profit, because it's just like it's highly seasonal. It has all these sort of like very predictable patterns to it, but those patterns need to be encoded in a way that allows the model to extrapolate them. When I see time series that come from more like physical processes, really high frequency stuff that jumps around, stuff with a lot of really abrupt changes in it which violate this like local smoothness idea, then you can kind of like see right away. Like my prior can be expressed as like looking at a time when someone shows me a time series and they're like, would Profit work on this? I know right away if it will or not. And it's a lot of it's just like knowing what human generated data looks like from having seen it a bunch of times.
So you're essentially encoding somehow like Earth human things like week and month and year. So it's designed for more like demand forecasting versus the position of Jupiter's moons. Is that fair?
Yeah, I think that's right. I think like when we first released Profit, Andrew Gelman on his blog was very flattering to get mentioned by him. He was like, I'll show you a time series that Profit won't do well for. And it was like some kind of like some physical process. I forget what it was. I think it was like lemur population or something like that. So it's like one of these like physical processes, like population ecology, where it has a kind of chaotic period to it because it has a feedback loop built into it. So the period is not regular, and it's like, well, if the period is not regular, then there's no way a model that's trying to learn a regular period structure is ever going to fit that. So I think we ended up sort of like having to admit that, yeah, sorry, Andrew, you can't forecast like lemur population using using Profit. But I think that we're fine with that. It's like it's an 80-20 thing. We'd like to capture the kinds of problems that we see in practice.
And so, can you say a little bit about what you're doing under the hood with Profit?
Yeah, there's probably like 2 or 3 tricks that I think add up to the whole thing. Probably the most important trick is just that we have these trend change points. So the actual profit forecasting model can be really simple. If you strip out the seasonality, it's just a piecewise linear regression. Making a linear regression extrapolate well is challenging because you don't really always know how much of the historical time series to use to fit the slope at the last point. So you're trying to go like into the future. You need to know the slope at that last point, where that's coming from. So what we do is we introduce this idea of that the slope can change at various points in the past, and that we prefer those changes to be sparse. So that we just use an L1 penalty in order to do that. So it's a really standard trick in machine learning. And what that does is it comes up with like a pretty, I would say, like parsimonious representation of the trend of the time series, which it's like a sequence of lines that fit together. And the last line segment is the slope into the future. And so that actually works quite well. And it's very similar to exponential smoothing procedures, which are sort of getting the local slope that you're trying to use to extrapolate from the more recent data rather than from the far past. It's just like a sparse version of that. So that's one big trick.
But then, how does that model periodic effects into the future, or is that not part of its
Oh yeah,
thing
so
that's trying to do?
the seasonality is just applied additively. So it's at its core, Profit is just a generalized additive model. So very similar to, a lot of GAM packages will fit all kinds of stuff that looks like Profit. It's just that they're not really designed to extrapolate well. So they interpolate well because that's what GAMS, the loss function for GAMS is kind of capturing that. For Profit, we sort of like had to make these modifications in order to get the extrapolation performance. And really, like, if you think about it, it's all about controlling the complexity of the model that you're fitting close to the boundary of the data, which is like, because it's extrapolation, you really don't want it to get overfit at the last part where you're trying to go past it. So in typical machine learning, we do way more interpolation than extrapolation. So we commonly don't think about controlling complexity at any particular point. We just want like the best model. But in forecasting, it's like you really prefer simple models when you're going off of the data that you've seen already.
Totally. I guess that's a good segue into one more topic I wanted to ask you about, which is election forecasting. And I think you've talked about or thought about election forecasting with using prediction markets, which is something that I think probably me and a lot of people listening to this have thought about. I guess I'm just curious. I mean, the question that's like top of mind right now, and this is probably going to be out of date as soon as we release this, is like, we have like 538 and all the election models, showing a really high percent chance for Biden compared to the prediction markets and the betting markets. Do you have any thoughts on how those two things have diverged and why?
Yeah, that's a really interesting question. I think the prediction market people, Dave Rothschild at MSR was like a really big believer in the prediction markets last cycle and has since switched over to polling. And I think he'd be a better person to tell you why prediction markets are failing to do this. But I think one part of it that I find interesting is that like prediction markets, I think one reasonable use case for them is to like do emotional hedging. So you could say like, oh man, it would be the worst thing in the world if Trump won. So I'm going to go bet every cent that I have on him winning in a prediction market, so that if he wins, I'm just going to win a lot of money. So not every prediction market participant is trying to like maximize earnings. They can be hedging, and it's a tool for hedging. So you might think of like, okay, so part of the difference in price could be suppressed because of
But shouldn't like some
the
kind of, I mean, I'm out of my depth here a little bit, but isn't there some kind of efficient market hypothesis that someone would sort of exploit the emotional hedging to make themselves a lot of money?
Yeah, that's true. If the constitution of the market were like, if you had an infinite population of traders, then yeah, I think you'd get there. But like without a lot of liquidity, if most of the people, all the market stuff depends on like having a lot of people, and they're all if you know a certain fraction of them are profit motivated, then I think you're good. But part of it is also transaction costs. So like it's not predict it, for instance, has like a 20% fee for removing, for taking your money out. So it's sort of like makes the incentives not quite the same as trading in a financial market. But yeah, I don't know. I think it's an interesting empirical puzzle, because also if you go to predict it and you look at the state level predictions, I think they align quite well with 538, but the aggregate one, it doesn't. And to me, that feels like the hedging explanation is my favorite way to explain it. But I don't have a
Well,
better
it sounds like
explanation
to me then
than
you're siding with the poll aggregation versus prediction markets.
Well, I am a big believer in polls. I think that like it's a really well understood technology that we've been deploying for a long time, and there's a lot of great science behind it. I think you see Elliot Morris at The Economist, working with Andrew Gelman and doing best of breed Bayesian modeling of the polls. At the end of the day, there's some. I think of this as like there's some latent variable, which is like intention to vote for one candidate or the other, that we're just getting noisy observations from. And when you have like a latent variable that you don't observe, you want to pool as much information that you have about that as you can, and you want to try to like debias it as much as you can. And we've gotten quite good at that. I think that the real kind of like epistemological problem here is like whether polls mean what we hope them to mean. I think like it might just be that people answer polls differently now or think about them differently. This was like the shy Trump voter hypothesis from 2016. Is like maybe people like legitimately aren't telling you how they're really going to vote. And if in a world where that breaks down, I think polls are become a lot less credible as a source of information. So I think we always have to take on faith that people are answering these things like in accordance with their beliefs, at least most of the time. I hope that will sustain itself, because I can't even really imagine a world like 4 years from now, 8 years from now, where we actually don't have any credible estimates of these things. We've sort of gotten used to feeling some level of certainty about where the election stands.
Well, I guess what role then, if you believe the polls, I guess what role would prediction markets play or could they play in election forecasting?
Certainly the polls are informing the participants of the prediction markets, right? Like I can't imagine that they're coming up with their beliefs. People in the prediction markets have some subjective belief about what's going to happen. That's informed by some information about the world, whether that's just them talking to their friends or like reading the news or whatever, or actually just like doing analyzing data. I think at the limit, if you really want to do well in a prediction market, you would want to bring as much information as you could to bear on the problem. But it also, I guess, this comes up a lot where it's kind of like maybe the people who analyze the data the most are not as willing to participate in the prediction markets. Like people are always calling on Nate Silver to make like large bets about about what he's estimated, and he seems like a little bit reticent about that. So I guess there is this interesting question of like maybe the polls aren't driving the prediction markets as much as you think. To be honest with you, I don't really know what's motivating a lot of the people participating in the prediction markets, and whether they're like really acting in a profit motivated way, or they're just kind of gaming. Like you can think about fantasy football players are doing a similar thing. They're kind of like moving some things around on the internet and hoping that they win a little bit of money as a result of it, but they might not be thinking too deeply about it. I'd love to see some research on just like actually talking to those people about what their process is and what they're doing. If you go to a website like Metaculus, which I'm a big fan of, it's sort of not a prediction market, but a prediction aggregator. You see like a really nice community of people there that actually talk about how they end up with the forecast that they came up with. And I think that you get a lot of insight from that, sort of like what are they actually doing in practice to figure out the future state of the world. And it does look a little bit like this, like foxes versus hedgehogs thing. So it's like they just kind of like cobble together little bits of information and make more directional changes.
Yeah, I mean, I guess you could imagine like, I mean, Nate Silver is so spectacularly good at articulating what he's doing, but you could imagine someone who's really good at forecasting, but maybe not as compelling of a writer or as clear of a thinker, doing really well in a prediction market, but not having a famous website. So it does seem like that that could provide them room to shine.
I was a big believer in it, and I think I'm just starting to have doubts now. I mean, I built a prediction market a few years ago because I thought that there were a lot of Nate Silver types out there doing this kind of stuff, and I guess I just didn't end up. It's really hard to get people to participate in prediction markets. I think this is an underrated aspect of it. Is like I built one. I tried to get people to use it. It's cognitively costly to create predictions, and especially ones where you're going to like bet some have some skin in the game, you're going to even incur more. So it's not free to get participation in a prediction market. They're doing computation in the background that's like expensive to produce their predictions. I think this is an underrated part of the problem, is that like in financial markets, we just assume that the incentives to participate far outweigh the costs to the participants. But in prediction markets, I think that the problems that they're solving are cognitively expensive and the payoffs are a little bit smaller. So we might be in a world where like we get sort of under participation. And so you don't end up with these like great stories about markets being amazing aggregators of all available information.
Totally. Well, we always end with two questions, and I want to give you some space to answer these questions. So our second to last question is, what's an underrated aspect of machine learning or data science that you think people should pay more attention to?
Yeah, that one I always have strong opinions about, and it's to me it's very obviously model comparison and evaluation. I think it's like we focus so much effort on training models, getting features, on all that crazy architectures. The space of models is that we can consider is increasing like rapidly, but we still are bottlenecked on like, is this model better than the one that we already had? And I think that that's a nuanced problem, and there's it's usually like a lot of criteria that go into that, and coming up with good model evaluation procedures is hard. It's not just like AUC, it's not precision recall curves. That's like a part of the problem, but there's just like so much more to model comparison, like cost of the model, upkeep, decay, stability, interpretability. Like, I mean, there's just like this wide array of things that we like about models that we're not really like encoding. So I just feel like it's always the thing that people, when I'm talking to them, have thought the least about, but it's the part that I'm most interested in. So that's my very clear answer to that one.
Interesting. Is there any work that you could point people to if they want to learn more about that?
I mean, I think that the posterior predictive check stuff in the Bayesian community is getting in the right direction. It's sort of a general approach to inspecting of the predictions that a model makes. You see actually in the Elliott Morris and Andrew Gelman doing this with their election probability model. It's like they're like looking at predictions and trying to like see, like, does this like make sense to me, and where can we make improvements? So I think that that's a really fruitful place to look. And I guess the other literature that I'd point people to is off policy evaluation. So usually if you have a model, you're going to go and make decisions with it at some point. Those decisions will add up to some value in some way. So the most faithful representation of how good a model is like if you actually like plugged it into your production system and ran an online test, how well would it do? So off policy evaluation is just sort of like an offline way to try to estimate what would happen online if you ran your model in production. And so that it's a hard approximation to make, but if you can do it, then you can be much more sure that your model is the right one for the task that you're going to deploy it for.
Interesting. I guess my final question is, what's the biggest practical challenge of making machine learning models useful in the real world? And I would say for you, like at Lyft, like what do you see as like the biggest bottleneck to taking a model from sort of like research or conception to used in production?
Good question. I think there's still a lot of like really base needs that need to be met. I think like getting training data into shape that the model can be trained on it, I think is still something that like we spend a lot of time just like making data sets for consumption of models. I think that that's something that's still a little bit slow. There's some technology that's helping there, like feature store type ideas. I think that that's a challenge. I think that this just like model lifecycle stuff is still a big thing. I think two people collaborating on a model is a pretty challenging thing these days. I think you see sort of like if one person gets to work alone, they can move much more quickly than they do in a group. But getting a group's worth of effort on a model is a really useful thing. So I think that decomposing the problem into something that multiple people can work on is a big opportunity. And finally, I think that like the monitoring and like kind of making sure that things are behaving the way that you'd like in production, like that trust when it's running in production. And for us at Lyft, it's like, if we screw this up, then the marketplace falls apart and drivers don't make money and riders don't get rides. It's like a really big downside risk to losing reliability. So getting to the point where we trust the decisions and that we end up spending a lot of time just making sure that we're confident that the models are going to do something reasonable in the real world, and a lot of layers of testing in between. And I think that in the future, I would hope that we can get to a point where that friction starts to go down and we can be a little bit more iterative.
Awesome. Well, great sentiment to end on. I really appreciate your time.
Yeah, Lucas, thanks for all the great questions. This is super fun.
Thanks for listening to another episode of Gradient Descent. Doing these interviews are a lot of fun, and it's especially fun for me when I can actually hear from the people that are listening to these episodes. So if you wouldn't mind leaving a comment and telling me what you think or starting a conversation, that would make me inspired to do more of these episodes. And also, if you wouldn't mind liking and subscribing, I'd appreciate that a lot.